Hey everyone, and welcome to PrepFusion. So today we'll be starting the lecture 6 of the time domain analysis. So before that, I gave you some assignment problems in the previous lecture. So we will solve those first, then we'll start our main topic of this lecture. Right? So what was the first assignment problem? This one was the first assignment problem. So in this question, we have to find the value of K for damping ratio is 0.5 for the given system. Okay, like I have to write if damping ratio is 0.5. okay, so damping ratio has been given, but I have to find this value of K. So you might say that yeah, my omega n is this omega n square is 2, so my omega n square is 2, right? And my omega n will be under root 2, and my what is this this is 2 zeta omega n, and this is equals to 1. Again, like when you try to solve this one equals to 1, so my zeta becomes 1 by 2 under 2, but the question has already given me that the zeta is 0.5. so how is it possible? So what is the wrong thing that I'm doing? Simply I didn't convert this into standard form. So let me first copy this one. Okay, let's copy this one and convert this into standard form. So how will I convert? Basically, right, I will get the characteristics equation of this one. So this is s square plus 2 zeta omega s plus omega n square. This is the standard equation, right? Standard equation equals to 0, characteristic equation. But here this is not in standard form, so this is not standard. So what I will do, I will convert this, right? I will take the K as common to make the coefficient of s square equals to 1. So s plus 2 divided by K, s square plus s by K plus 2 by K. Okay, and I have K here. So now this is the standard format. Okay, so here I can compare my omega n and this constant term, right? So the numerator doesn't matter. Okay, I am only interested in the denominator. So it is basically, right, omega n square equals to 2 by K. So omega n will be under root 2 by K. Okay, now what the question has told us is that my zeta, okay, damping ratio is 0.5. so 2 times zeta omega n will be equals to this term, right, 1 by K, coefficient of s basically. So it is 1 by K, so this is equals to 2 into 0.5 into omega n is under root 2 by K. Okay, and this is 1 by K. So what do I get? Basically equating this one, my under root K equals to under root 2, so my K equals to 2, right? K is equals to 2. So yeah, this is my answer basically. Okay, so that previous one you shouldn't do, right? Just blindly see this and you write this constant term as omega n square. That you can't do. Obviously you have to check whether this is in standard format or not. We have already done few sums before this. Okay, so now let's go to the another question. This is the another question. This question is a gate question. What it is telling is that we have to find the unit step response y of t of a unity feedback system with open loop transfer function gh equals to this one, and the value of K is this one. Okay, so like we have to find the value of K basically if the open loop transfer function is given and the unit step response of a unity feedback system is given. Okay, so this is the unit step response. Now obviously from here, right, this is a third order system, so I won't be able to comment much, but I can see there are oscillations, so I won't be able to comment much on damping and all those things. But what I can comment on is the steady state value. Okay, so if somehow I find the steady state value and equate this with this 0.8, then I will be able to get the value of K, right? Okay, get the value of K. So basically what I will do is first I will write the transfer function, like the closed loop transfer function. Okay, that's how I will find the relation between input and output, right? So at input I am giving a step, so let's see what I am getting at the output. So my closed loop transfer function CLTF equals to GHS upon 1 plus GHS. So it is simply K by S plus 1 whole square into S plus 2 divided by 1 plus GHS, right? It is unity feedback, so H is 1 only. So K by S plus 1 into S plus 2 whole square. So this is equals to K S plus 1 whole square S plus 2 plus K. Okay, so this is my closed loop transfer function, right? So here what I will do now, this is equals to my C of S upon H of S, right? So now what I will do, I will simply not H, sorry, C of S upon R of S. So my R of S is 1 over S, so R of S equals to this one. So I'll copy this one. So it is a unit step only. So basically, right, now I will simply multiply this C of S equals to K by S into S plus 1 whole square into S plus 2 plus K. Okay, now what do I know? I know the steady state value of this output, right? Y of t. Okay, this is written Y of t, so I have to write Y of t here. Sorry, so we'll write Y to go with the convention, right? Y, and this is Y. Okay, so at the basically at the output, the constant value is only 0.8, right? So if I find a steady state value, okay, and apply the final value theorem, then I will be able to solve this. So applying, as the system is stable, right, it is settling to some value, so hence I can apply the final value theorem. Okay, that my Y of infinity equals to limit S tending to 0 S of Y of S. So this 1 by S gets cancelled, right? 1 by S gets cancelled. I am multiplying S, 1 by S will get cancelled. I will be remained with this term. So it will be simply K by what is this, 1 into 2 plus K. Okay, so now this, right? So what is my Y of infinity? Y of infinity is 0.8. okay, so only this information is given, right? Anything else I am not able to tell. There are 3 oscillations, but with that I won't be able to do much, right? So my Y of infinity is 0.8, so this is, I can replace at 0.8, this is K by 2 plus K. Okay, this is 4 by 5 basically. So this is 8 plus 4K equals to 5K. So my K value equals to 8, right? So my K becomes 8. So K value becomes 8. So now, right, I got the answer. So this is basically the answer. Okay, nothing else. So I hope you understood like how to apply this and all. So only one hint is given, right? Here we use the data. So you see the question and see like what data has been given to you. So according to that you use that, right? Use that. So yeah, this was the solution for this question. Now let's solve for another question. So this is another question. So here, right, a differential equation is given and says that it describes a system with an input x of t and an output y of t. The system, which is initially relaxed, is excited by a unit step input. System was initially relaxed, but after that we give it a unit step input. Then the output y of t can be represented by which waveform? Okay, that we have to tell. So like whenever you see these types of question, you observe the diagrams, right? So what do you observe? Okay, is anything odd out of all these 4? There is, right? This is going unstable and all the other ones are stable, right? Other ones are stable, but this is going unstable. So if I can just check if my system is stable or unstable, From there I can understand that if it's unstable, then it's definitely option A, and if it's stable, then I have to check. Okay, then I have to check whether this is like a over damped. Okay, this is reaching slowly, this is like critical damped, reaching very fast without any oscillation, and this is like an under damped. Okay, so we'll have to check according to that if my system is stable. Now, like obviously I know this, so I can just see the question and tell. So can you do one thing, like we will study this in Routh-Hurwitz criteria in the next chapter, but I'm telling you, if all the coefficients of my terms, right, this differential equation is positive, then my system will always be almost be stable, right? Almost be stable, except like, they are positive, right? They are positive. If they are positive, then they will be always stable. If one of them is negative, right, one of them is negative, then it will be unstable. We will study this in Routh-Hurwitz criteria. Okay, there you will see. So from the coefficient itself, I understood that my system will be unstable. So if I apply it some input, okay, unit step input, it will rise off. So option A will be my answer. Okay, so this is how you solve quickly. Okay, now let's solve it obviously normal in calculation, right? So what is my transfer function given? My transfer function is yfs upon r of s, right? Yfs upon basically input is this is the input, right? X is the input. So like what I can do, I can take the Laplace transform this differential equation. Okay, I will do this in short. I will take the Laplace transform of this differential equation. I will ignore the initial conditions, okay, as like initial, this is 0, okay, output is 0, so I will ignore the initial condition. So now what I will do, as it says, right, the system is initially relaxed, so I can ignore them. So the Laplace transform of this one will be 100s square, Laplace transform of this one will be 20s, and this is 1. So I get 100s square minus 20s plus 1. So this is what I get basically. Okay, so now right now what is the numerator? It is 1 only. So what else do I get? Basically, right, it is I will take the 100 common. Okay, take the 100 common. Like now I have to find the location of the poles. If they are on the right hand side, then it is unstable. If they are on the left hand side, then it is stable. So if I take 100 common, this is s square minus s by 5 plus 1 by 100. Okay, so yeah, this is like a perfect square example, right? So this is like a perfect square example. This is 1 by 100, and this is s minus 1 by 10 whole square. So what I can see repeated poles. Okay, I can see repeated poles at the right hand side, or what I can say, the zeta is negative. That also I can say sp equals to repeated poles on the right hand side, and zeta is negative. System is unstable. From here also I can say, right? So that's why this is going up. Okay, this is going up. There is no like limit. So from here I can eliminate the options. Else if it would have came stable, then you have to check for the value of zeta. The value of zeta will be 0 to 1 for this one, because this is under damped. It is oscillating. Okay, then it is reaching steady state. The value of zeta for this one will be exactly equals to 1, because this is reaching a steady state very fast. Okay, as like I can see, okay, which is reaching steady state very fast, it is difficult to tell. Okay, but okay, I think this is acting as a first order circuit, and this is okay, this is difficult to tell. I think this is reaching the steady state much faster. Okay, from here I can't visually tell. Okay, but whichever will reach steady state much faster, that will be my critical damp. Okay, and it will have no oscillation, and whichever will reach steady state slower, that will be my over damped, and it also don't have any oscillations. Okay, so yeah, that was basically it for this question. Now let's solve for this question. So this question is very interesting, where is also another gate question. So what is this question telling us? The output of a standard second order system for a unit step input is given like this one. So the output of a standard second order system is given like this one. We have to find the transfer function of the system. Okay, for this. So one option is obviously you can take the Laplace inverse, okay, of this one, then solve for this. That you can do. Okay, no issues. But can you solve it a bit quicker? So it's like 2 AM at the night. Sorry. But can we solve it a bit quicker, right? So how to solve it a bit quicker? So what you can do is, we know the standard form of a second order system for underdamped condition. This is a underdamped condition, right? So this is not possible, okay, because this is a standard form of underdamped condition. So this form is not possible, right? This is gone. Okay, this is gone. Now is this form possible? This form is also not possible, right? Why? Because this is s plus 1 whole square. So I have two roots at s equals to minus 1. This is critical damped, okay. So for critical damped I get something t raised to minus t. So this is also not possible, and this is under damped, okay. Sorry, this is over damped. So this is also not possible, okay. What am I left with? I'm left with this and this, okay. Now these two are difficult. These two are difficult, right? So for this one, what do I see? I see that my this is omega n. This omega n is under root 3, because omega n square equals 3, and this is another omega n. So my omega n square equals to 4, right? Omega n square equals to 4. So omega n equals to 2, right? So yeah, from here telling this one is difficult, but if I find the damping frequency, then I will be able to relate with this one, right? Okay, under root 3. So if this one has damping frequency of under root 3, then this will be my answer, and if this one has, this will be my answer. So from these two, right, I can find my basically damping frequency, okay. So damping frequency, basically method 1 is checking options, right? Method 1 is options. So first one, which is option A, over damped, hence it is eliminated. Second one is critically damped, okay, hence it is also eliminated. And my third one is, what is the third one? Third one is my this is under damped, right? So this can be under damped, this can be my answer. And fourth one is okay, also under damped. So I don't know about this one yet, okay. These are all question marks, okay. So I have to check. So now, right, what I will do is basically find the damping frequency of C. So normal my C of my y of t has damping frequency of y of t has omega d equals to under root 3. And right now, what is my omega d for option C, right? So first I will find omega n for option C. Omega n equals to omega n square equals to 3, right? So omega n equals to under root 3. So this is not possible anyways. If omega n is this one, so zeta, like what is my damping frequency formula? It is omega d equals to omega n under root 1 minus zeta square. So it will be something less than under root 3. So this is not my answer anyways, okay. So from here I can stop, but still I will derive it. What is my like zeta? So I will equate 2 zeta omega n equals to this term, so which is equals to 2, right? So this equals 2, so this will be 2, and omega n is under root 3, so zeta will be equals to 1 by under root 3, okay, 1 by under root 3, right? So zeta is 1 by under root 3, so what I will write, omega n into 1 minus 1 by 3, okay. This is equals to omega d. So this is omega n under root 2 by 3, okay. So as you can see that this is something less, right? Okay, this is something less than like, what is my omega n? Omega n is under root 3, right? So it becomes under root 2, but I want my omega d to be under root 3, so this is not my answer, okay. Now let's check for the other one, right? So obviously I could have stopped much earlier, but just to show it to you guys that what is actually omega d coming. So now let's check the option D. If I check the option D, what I can see is the omega n square equals to 4, right? Omega n square equals to 4. So omega n square equals to 4, right? So omega n square equals to 4, then my omega n equals to 2, right? Omega n equals to 2. Now my 2 zeta omega n, what is that? 2 zeta omega n equals to 4, it is given, okay. The coefficient, no, not 4, 2 zeta omega n equals to 2, so it will be 2. So zeta will be 1 by 2 basically. Zeta will be 1 by 2. So now obviously replace this here. So omega d equals to omega n under root 1 minus zeta square, which is equals to, what is omega n is 2 and zeta square is 1 by 4. So this becomes 2 under root 3 by 2. So this becomes under root 3. So which is my desired omega d, right? So hence this one satisfies. So here option D will be my answer. Okay, can we solve this in another way? Can we find this directly without checking the options? So what I can do is use the formula of what do you say, damping factor and omega n, right? So now what we'll do is basically method 2. So method 2, what we'll do, we'll find the angle of inclination and zeta and omega n from the transfer, from the that response itself. Okay, time domain response itself. So this is zeta omega n. But before that, what I am observing is this, right? This is not in my standard format, right? This is some cos. So change it to sine. I have to change it to sine, okay, for proper angle of inclination, right? Because there theta was defined as sine only. Okay, so basically, right, what is this? I have written this relationship much more times. So this is basically my cos omega t equals to sine omega t plus pi by 2. Okay, sine omega t plus pi by 2. So yeah, now right, I will replace that theta angle like cos omega t equals to sine omega t plus pi by 2. I will replace that. So my y of t, what will it become? 1 will remain 1 minus this 2 by root 3 e raised to power minus t. Okay, then sine root 3t, sine root 3t. Okay, then this will be pi by 6 plus pi by 2 minus pi by 6 plus pi by 2. So this is minus pi by 6 and plus pi by 2, right? So this becomes y of t equals to 1 minus 2 by root 3 a square minus t upon sine root 3t, and this becomes basically minus pi by 3, right? Not minus, sorry, plus pi by 3. Okay, so this is my standard format. Now from here what I can see, like this is my theta, right? This is my theta. So what I can write my theta as, so theta equals to cos inverse zeta, right? Okay, so cos theta will be zeta, that I know already. So zeta will be equals to cos theta, which is equals to cos of pi by 3. So what is this equals to? This is equals to 1 by 2. So zeta I get as 1 by 2, right? So zeta I get 1 by 2. Now what is omega n? So how can I compare the omega n? So what do you know? Okay, this was the previous. So what do you know? So this one, right? This like power term is that basically the time constant. We will understand this while studying the performance of the time domain parameters, but like performance parameters of second order circuits. But this is known as the time constant, which is zeta omega n. So here, right, zeta omega n comes. So I will copy this and explain then. This one is my zeta omega n, right? Okay, so what is my zeta? Zeta is half, right? Zeta is half. So if my zeta is half and omega n I don't know, which is equals to 1 itself. So omega n equals to 2. Okay, omega n equals to 2. So now I can write the equation from here itself, right? So DC gain, how can I know DC gain? So DC gain is difficult to understand it. So how will I equate the DC gain? So for DC gain, right, what you will understand is you find the C of infinity and you have given a unit step, right? That you know, that you have given a unit step input and you find my y of infinity, and from there you will get the relationship between the DC gain. Let me write, then you will understand. So how will my transfer function look like? So my transfer function will look like something this is k omega n square divided by s square plus 2 zeta omega ns plus omega n square, okay, plus omega n square. So yeah, this is basically this one, okay. So now let's check what is my output response for this one. So I am giving a unit step. So my C of S will be, okay, is this C or Y? This is Y, so I will not write C, I will write Y. Y of S equals to 1 over S into k omega n square divided by s square plus 2 zeta omega ns plus omega n square, right? So this is basically my response. Now what is my y of infinity? Y of infinity, right? Let me take another page. So my y in time domain of infinity equals to simply again limit as s tending to 0 as y of s, okay. So this ss will get cancelled, okay. I will be left with this one 0, this one 0, so it will be omega n square by omega n square k equals to this t of s, sorry, y of s. So it will be k omega n square divided by omega n square. Now what is my y of infinity? My y of infinity, here what I can see, what is my y of infinity? My y of infinity is 1, so my k will be 1 only, okay. So that may cause a bit of confusion, right? That's why we can solve it like this one. So my y of infinity will be 1. So k is equals to 1 itself. That is not an issue. So I get k, I know zeta, I know omega n. What else do I need? I need nothing, right? So everything is done. But a is not known, but a is unit step, okay. That is the amplitude. So a is also known, right? It is unit step. So it will be 1. So my transfer function, okay, will become basically what do you say, omega n square, which is 4 divided by s square plus 2 zeta omega n s, oh not zeta, sorry, zeta is 1 by 2 and omega n is 2, so it will be only 1, right? So this is s square plus 2s plus 4, okay. So yeah, this is my transfer function, okay. So now, right, can I solve this using any other method? So there is another method, okay. The other method is basically with the help of omega d, right? With the help of omega d and omega n. So like this is my omega d, okay. So let me write this in third method. So in third method, how will you solve? So basically, right, what is the omega d is root 3, okay. Omega d is root 3, and I know zeta omega n equals to 1, right? That I know already from previous method, I know. So my omega n will be simply the square of under root of square of this 2, okay. So it will be omega d square plus zeta omega n whole square. So what is this? This is equals to 3 plus 1, so this is equals to 2. So this is 2 radian per second, right? This is 2 radian per second. So this is my omega n. Now, right, now I got the omega n, I know the omega d, and I can find the zeta from here. So then my zeta, okay, will be simply 1 by omega n, which is 1 by 2, okay. So yeah, I know all this thing. Again, put this in this transfer function, but you have to follow the same step again, okay. Follow the same step again, okay. That you have to find the DC gain, okay. Find DC gain. Find DC gain. And after finding the DC gain, what you will do? You will get this expression, right? Okay. You get this expression. So yeah, this was basically it for this question. We analyze this using 3 methods, but sometimes what will happen is some method is working and some method is not working, so you just have to be a little bit careful, right? So now let's start our lecture, that is lecture 6. So in this lecture, what we'll do, we'll understand the effect of zeros in a system, okay, and we'll also understand the time domain performance parameters of first order systems, okay. So let's start with effect of zeros, okay. So what effect does zeros give in our system, okay? If you have some zeros, then what changes will I see, okay? And if you don't have that zero, then what will happen? So if I have some zero, right, like here I've given you some question, find the step response, this is unit step only, okay, no worries, for the following transfer functions. So one is this one and one is this one. Now you stop this video and like pause this video and solve it, okay. Check how are my step response for this one and this one. So what is the difference between these two? I have a 0 here at s equals to -2 and I don't have a 0. So yeah, let's start our solution. So one thing to note here is, basically don't use the dominant pole approximation, because if you use that, then we won't be able to see what is happening, right? So this time calculate this without the use of dominant pole approximation, okay. So yeah, now let me solve for the first one. So for the first one, my transfer function is this one, right, 1 by s plus 1 into s plus 8, okay. So basically it will become c by r of s, right? C by c, whatever output you want to say. So I will say c by r. So r is 1 over this time. So r of s is 1 over s, okay. So what is my y of s equals to? My y of s equals to simply 1 over s divided by s plus 1 into s plus 8. Now again, right, we will use the partial fraction decomposition, right? So if I partial fraction decomposition, what do I get? So basically, right, if I put s equals to 0 and multiply with s here, so this will be left. This is known as the residue. This we will learn in mathematics also. So I put s equal to 0. This becomes so I will write this time. So 1 by 0 plus 1, okay, into 0 plus 8. So this becomes 1 by 8. So this is 1 by 8 by s, okay. Now what is the next? I put s equals to -1. Obviously I multiply s plus 1, so this one gets cancelled. I'm left with 1 by s and this 1 by s plus 8. So if I put s equals to -1, I get 1 by -1 into 1 by 7, okay. So what do I get? I get -1 by 7. So this one will be -1 by 7 by s, okay. And if I put s equals to -8, what do I get? If I put s equals to -8, I get 1 by -8 into 1 by -7, right? So this becomes plus 1 by 56. So okay, this is s plus 1 and this is plus 1 by 56, s plus 8, right? S plus 8, okay. So yeah, this is basically my y of s. Now let's take the Laplace inverse. So this is actually a bit like congested here. So this is this. So this is now I'll take the Laplace inverse. So this is equals to 1 over it minus 1 by 7 e raised to power minus t plus e raised to power minus 80, okay. So this is my time response. Now what I'll do, I'll solve for the second one, okay. So for the second one, what do I get? So I'll take another page actually, okay. Let's solve for the second one. What is the second one? Second one is this one, right? So what will be my y of s? So y of s will be, the poles are same, right? Just I have a 0 at s plus 2, 0 at s equals to minus 2. So poles are same, s plus 1 into s plus 8. Okay, s plus 1 into s plus 8. So this is my y of s. So now what I will do, I will again do the partial fraction decomposition. Okay, so this time it will be a bit different. So I will put s equals to 0 and multiply by s. So what I get 2 by 0 plus 1 into 0 plus 8, right? So this becomes 1 by 4. So I am getting here 1 by 4s. Now what I will do, I will again put s equals to minus 1 and multiply by s plus 1. So this will be 1 divided by minus 1 into 7. So this is again minus 1 by 7. Okay, this doesn't change, s plus 1 remains same, right? Now what I will do, I will put s equals to minus 8, right? S equals to minus 8. So if I put s equals to minus 8, what do I get? This I get as 1 by 8 minus 8 into here minus 6, and here this is minus 7, right? So this is 1 by minus 8 minus 6 and minus 7. So now what is the result? Result is simply minus 6 by 56, right? Which is equals to which is divided by s plus 8 also. Okay, so this is my y of s, right? This is my y of s. So now let's take the Laplace inverse of this one. So if I take the Laplace inverse, what do I get? This is 1 by 4 minus 1 by 7 e raised to power minus t minus 6 by 50 e raised to power minus 80. Okay, so this is my basically y of t, the output. Now I have plotted these two, and let's check what is the difference between these two. So what I have plotted is basically I plotted these two magnitude functions, right? These two. Okay, because this is the steady state, I don't care about this one. Okay, the steady state I don't care. Okay, what I care about is the dynamic response. Okay, dynamic response I care about. That's why these are the dynamic response, right? Steady state it will reach anyways, that depends, because 0 also like defined a bit of DC gain also, so that is different, but I am more concerned with the dynamic response. So what I have plotted, so basically, right, I plotted this one. Okay, this is the basically this function I have multiplied this with 8. So I will write this one as 1 by 7 e raised to power minus t, then plus this in blue, this is plus 1 by 56 e raised to power minus 80. So one thing to note here is I just want to take compare this in terms of magnitude only. Okay, sign I don't care, I will compare this in terms of magnitude. Why? You'll understand. So this is basically not plus, sorry, this is versus this one, right? Okay, so what thing do I notice here? And this one is the same thing here, but here the magnitudes have changed. Okay, this is now this 1 by 56 has changed to 6 by 56, changed to 6 by 56, right? So this 1 by 56 has changed to 6 by 56. Yeah, so yeah, this has changed to 6 by 56, right? So like what is the difference you see? The difference that you see is that this, right, like this was the pole that we used to ignore, right, in dominant pole approximation. So here I can see this is minimally affecting my dynamic response, right, not affecting my dynamic response. But when I introduce a 0, okay, when I introduce a 0 at s equals to minus 2, this is getting more dominant. Okay, this is getting more closer to my dominant pole. Okay, so my dominant pole has reduced its dominancy, so the dominance has been reduced. Okay, so the dominance of pole at s equals to minus 1 has reduced. Okay, the dominant s equals to minus 1 has reduced due to what? Due to addition of a 0. So this is basically the effect of a 0. What it does is if we introduce a 0, the dominance of this -1 pole is getting reduced. Okay, so due to introduction of the 0, the dominance has been reduced. So okay, so this is the basic like thing that the 0 does, right? It changes the behavior, dynamic behavior of the system. So here also I have written that 0 affects the dynamic okay, zeros affect the dynamic, or like what you know is transient response of the system. That is, it changes the amplitude of the response, but it does not affect the stability. It is still stable, right? But here what I should mention is, like yeah, 0 doesn't affect stability. Okay, system will be stable no matter what, system is stable anyways. 0 does not affect stability, but what does it affect is, it affects the transient behavior. So steady state, it doesn't matter. Okay, like it will be stable. If it was previously stable, adding a 0 will not make it unstable. But by dynamic behavior, right, if you write the unit step response, there you will see that this pole is getting more dominated. Okay, so this will differ. Okay, this due to this 0, the dominance of this pole will be reduced. Okay, -1 will be reduced. Okay, we can't simply ignore that right now. Okay, so that is what a 0 does. Also, what does zeros help us? Zeros help us to remove the effect of a pole by using pole zero cancellation. So like, what does this mean? So if I make this 0, okay, I'm getting closer to this -1, right? If I absolutely get this 0 to -1, what will happen? The effect of this pole will be completely vanished. Effect of this pole will be completely vanished. So that is what 0 does, right? If I place this 0 near to this -8, what will happen? I will have s plus 8 at the top and s plus 8 at the bottom. That will get cancelled. So yeah, that is basically what a 0 does. Whichever it goes closer to, it makes it weaker. So be careful of those things. So whichever thing it touches, right, it makes it weaker. So yeah, that is what a 0 does. So basically, to cancel a pole, basically we have to exactly go at that location. Okay, location of the pole, and it will totally nullify the effect of pole, right? So yeah, that is what a 0 does. Now another thing. Now this was for the left hand side. If my 0 was at the left hand side of the g omega axis. Now if my 0 is at the right hand side of the g omega axis, then what will happen? So again, I have taken one example. Here my 0 is at s equals to +2. So let me break this down. Like, I have to find the step response for the following transfer function. Okay, so a transfer function is y of s over r of s. So r of s is 1 by s. So this will go, okay, sorry, I will not transfer function, not right. S minus 2 s plus 1 into s plus 8. Okay, so this is my output, right? This is my output. So again, let's do the partial fraction again. So this time I will put s equals to 0. So what do I get? -2 1 into 8. So this is -1 by 4. Base. Okay, now if I put s equals to -1, if I put s equals to -1, I get 7, and this is -1. So this is -7, right? -7, and this is -1, I get -3. So this is -3 by 7. Okay, let me put it here. This is -3, and this is -1, and this is -7. So this is basically okay, -1 I put, sorry, this is +7 actually, sorry, this is +7. So this is 3 by 7. Minus minus cancel each other out. So this is 3 by 7 by s plus 1. Now what else do I get? Now this, right, this is, I put s equals to -8. If I put s equals to -8, I get here -8 is this -10 divided by -8 into -7. So what does this become? This becomes 10 by 56, -10 by 56, -10 by 56. Okay, and this is s plus 8. Okay, again this is becoming messy, so I'll take this to the next page actually. This is what my y of s equals to. So what will be my basically did I do the Laplace sign over there? It's a mistake. Yeah, Laplace sign. So what will be my Laplace inverse of this in time domain, right? What will be my output? It will be minus 1 by 4 plus 3 by 7 e raised to power minus t minus 10 by 56 e raised to power minus 80. Okay, so yeah, this is my output basically. So now what I will do, I will convert this into some standard format. So I will make denominators of all of them same, so that I can compare each of the coefficients, right? So this will be, I will multiply this one with 14, okay, minus 14 by 56, okay. This will be with 8 e raised to power 24 by 56 e raised to power minus t minus 10 by 56 e raised to power minus 80, okay. So yeah, this is basically it. Now I have plotted the output waveform. This will be my time response. You might ask, why is this time response? Why the time response is like this? So what is happening is, initially this positive exponential is dominating, okay. Initially this positive exponential is obviously dominating, and this has higher magnitude. So initially, like, this is the steady state. The steady state, it will go to 0. I am not 0, minus 2 by 8, okay. But initially, as this is dominating, it will get added with this one, so it will rise somewhat. Then my sign will change, okay. So then it will remain same. So 0 at the right hand side changes the direction of my response, okay. So time response basically. So this is why is this harmful. I will explain you, okay. But let me write here, okay. Changes the direction of my time response, okay. Which is actually not good, okay. Which is actually not either in positive direction or negative direction. Basically the sign, direction means the sign, right? So why is this not good? Okay, let me say, like, write it here, like here, direction change, right? Direction change. So why is this very dangerous? So let's say, like, our fan, right? So if you turn on the fan, it is supposed to rotate in some direction. I don't know if it's clockwise or anti-clockwise, okay. So it rotates in some direction, but let's say your transformation or system has some pole 0 at right hand side. So what will happen? Basically the fan will start rotating in the opposite direction, and then it will again reverse rotate, right? So that may damage the motor, that may be very dangerous. Let's say in washing machine also, washing machine rotates in both directions, that is fine. But let's say in some other application, okay, where it is required that it rotates in one direction only, but due to something the 0 came, and due to the 0 my fan will start rotating in the opposite direction. Then, like here, it will first start rotating in the opposite direction, then it will rotate in its correct direction. So that is very harmful, right? That is very harmful. So yeah, that is the thing. So we have to be very careful about that, okay. So that is another effect that the 0 causes, okay. So like these type of things, right? Zeros in the right up plane of the geometric axis are known as non-minimum phase systems, okay. These type of systems. So of geometric axis right half plane of the geometric axis are known as non-minimum phase system. Okay, so this is what basically, or you can say non-minimum phase zero. So basically any type of system which has right at pole or zeros, okay, then it is known as non-minimum phase system. This will be understanding like border plot, but here I will say, like, as this is explicitly for zeros, I will write zeros here. Okay. So you can call it like, okay, let me write this poles and zeros, then it will be not then explicit. It will be okay. So yeah, this is basically about the zeros. Now let's quickly wrap up the performance parameter of first order system. So it is very easy, only we have only 3 parameters, right? So let's start. So yeah, these are the performance parameter of first order systems. So as number of poles is 1, so it will be rather easy. So this is basically the block diagram that we already know. This is the governing equation where tau is the time constant, only one varying parameter. We are not taking those other first order models, right? That one with delay and DC again I'm not taking. Okay, it's normal, simple, this one standard parameter. So now this is my, like, what I will do, I will check for the parameters for the unit step response. Now you might ask, sir, why are you checking for unit step response? You may have checked for impulse response also, you may have checked for parabolic or ramp also. So the problem with impulse is there is no constant input. I just apply some input and it just goes away. Okay, it just goes away. So for impulse, I won't be able to analyze my system parameters. I apply some input and it just goes away. I won't be able to analyze, right? As I will not getting any signal. Okay, at steady state I will not getting any signal. Okay, so that is for impulse. Now what is for the ramp and parabolic? So ramp in itself is not stable, right? Stable signal. So if I apply unstable signal, my output will also be unbounded. So that is of no use to me. That I can quantify or measure. Okay, unbounded signals I can't measure. Okay, I have some range, particular measurement of range, right? So that I have to take care of. Okay, that is one thing. Parabolic also is unstable. So those two signals are unstable. That's why I don't analyze my system with that. I analyze with only unit step. Okay, so again, unit step gives a stable bounded input and gives a bounded output. Okay, so this time my R of t will be U of t. So my R of s equals to 1 over s. Okay, and what is it? This is my step response. Sorry. So this is my step response. So basically, like, what is my step response? C of t equals to, so we'll do this quickly, we already know all this, right? What is the transfer function? Transfer function is g by 1 plus ch. So it is simply 1 by s tau by 1 plus 1 by s tau. So it becomes 1 by 1 plus s tau. Okay, so this is my transfer function. Now what is my output, right? Output is 1 by s times this one. C of s equals to 1 by s times 1 plus s tau. And what is the Laplace inverse of this? So I will not break this down because this is like this is what is it? We have mugged this one up, so we don't want to mug, but this is like the basic one, right? So you should know this one. This is C of t equals to 1 minus e raised to minus t upon tau into u of t. This is my response, step response. So, and the response looks something like this, right? Response looks something like this. Now one thing to note here is, if I apply, instead of a unit step, apply a step of a magnitude and also my system has a decision of k, then what will my output? So if r of t equals to a u of t, if r of t equals to a u of t and I have DC gain, okay, and DC gain of k, then what will happen? Basically my transfer function will become k upon 1 plus s tau. Okay, so my output C of s, what will it become? It will be a upon s into k upon 1 plus s tau. So again, if I do the Laplace inverse of this one, only the, as is a simple linear system, so I will get only C of t here, and this will be a k into simply 1 e raised to minus t upon tau into u of t. Okay, so this is basically my transfer function, right? This is basically my transfer function. I mean, not, this is basically my response. So simply this ak will be scaled. Okay, this you have to keep in mind. Okay, in like second order system also, this you have to keep in mind. Okay, so yeah, so always the generalized cases, if nothing is set, obviously we'll assume that it is unit step and the DC gain is 1. Now if something is set, then the generalized formula will be like this. Okay, keep this in mind. So first parameter that we'll study is the rise time. Okay, so what do you mean by rise time? So like for different responses, the rise time definition will change. So keep this in mind. According to our responses or according to our system, the definition will change. This is valid for the first order system. So rise time, this definition is valid for the first order system. Okay, what is the definition? It is the time taken for the system, that is the output of the response, to reach from 10% to 90% of its final value for the first time. Okay, not for the first time because this is not oscillating. Okay, this is not for the first time because this was for the second order system. Reach from 10% to 90% of its final value, right? So yeah, this is basically what my rise time definition is. So what in graphically what I can see is this, right? This is 0.1. No, this is not 0.1. Sorry, this is my, let's say this is my T1 where my response reaches 0.1 of AK, right? Response reaches 0.1 of AK. And this is my T2 where my response reaches 0.9 of AK. Okay, so this is basically the 10% of final value, that is this one is the final value, right? I will compare with the final value. So 10% of the final value and the 90% of the final value, and like this T is some T2, let's say. Okay, so what will be my like time? It will be TR. It will be TR. Okay, so this is the rise time basically. So now how to calculate this one? So we'll derive this one, right? So my CT, what is CT? CT is AK 1 minus e raised to power minus t upon tau. Okay, this is my CT. Now at C of T1, my output is 0.1 AK. So this is AK only. Okay, 1 minus, I will replace with T, I will replace T1 and this will be tau. Okay, so my e raised to power T1 minus T1 divided by tau equals to AK will get cancelled. Okay, and this will be simply 0.9. Okay, now what is for the other case? For T2, right? This one was the first case, and for the second case, when I am reaching 0.9 AK, so this time my T will be T2 by tau. Okay, so this is cancels out, so this becomes e raised to power minus T2 by tau equals to 0.1. Okay, so this is my basically this one exponential. So now, right, now what I can do, I can divide these two, right? Simply divide these two. What do you get? So simply if I divide these two, so I will divide, okay, this is 1 and this is 2, so I will divide, go to the next page. Two divided by 1, no, sorry, 1 divided by 2. Okay, so if I do 1 divided by 2, what do you get? So I get e raised to power T2 minus T1 divided by tau equals to simply what do you say, 0.9 by 0.1, which is 9. Okay, so now what is T2 minus T1? T2 minus T1 is this, right? T2 minus T1 is T rise. Okay, so this is e raised to power TR by tau equals to 9. Now what I will do, I will take the natural log on both sides. So if I take the natural log on both sides, okay, this will be TR equals to tau ln of 9. Okay, and TR equals to 2.2. okay, this I have already like calculated, and this is a standard thing also. So this is 2.2 times tau. Okay, So but if you don't remember, right, you just remember the definition and put it into the gate calculator, and there you will find, okay, just put ln 9 and there you will find that this is equals to 2.2. So yeah, that is one thing if you don't remember, because sometimes remembering all the formulas is difficult, right? Just remember the basic definition and put it in gate calculator, you will get the answer, right? So what you have to do, just you come until this stage and you put ln 9 in gate calculator and you will get your answer, right? So yeah, according to that you do whatever suits you, right? Now the next definition, next parameter is the delay time. Okay, so all of this basically measure the dynamic behavior of the system. As you can see, right, dynamic behavior, so zeros, right, they will also affect this behavior, right? Okay, that's why I taught you that effect of zeros. So now this is the delay time, right? So what does a delay time do? Delay time is the time taken for the system or the output slash response to reach 0% to 50% of the final value. So this definition is for this case. Okay, so it is basically for this first order unit step response. Okay, it is a time taken for the system to reach from 0% to 50% of final value. Okay, to reach from to 50%, right? So it is starting from 0 and let's say 50% is at this point. Okay, this is 0.5 ak and let's say this is some time td. So I have to find td. What do you do? Again the same thing, right? Only you just simply put that in equation and you will find td, right? So again, right, same thing only. My c of t equals to ak 1 minus e raised to power minus t upon tau. So I put c of t equals to 0.5 ak equals to ak into 1 minus e raised to power minus t upon tau. Okay, so this will become e raised to power minus, okay, this is td actually, sorry, this is td. .5. So my td equals to simply tau ln2. Okay, td is equals to tau ln2. Now what is ln2? ln2 is you check it in calculator, it will come out to be something around 0.7, 0.693. So this will be 0.693. okay, this if you remember, well and good. If you don't, again put this into calculator and you will get right in like 5 seconds, you will get your answer. So this is basically my td, right? This is basically my td. Okay, so yeah, we got this answer. Now let's go for the another parameter. This is the last parameter, which is the settling time. So what does the settling time mean? So settling time, now it has multiple definitions, so we'll go according to that. So the standard definition I will say to you first. So the time taken for the system slash the output, like to reach from 0% to some percentage of its final value. Okay, so from 0% to reach some percentage of a final value, that is known as the settling time. Now what this state says is that we have to be within the desired error band, whatever it has asked us to. So what is the desired error band? So these are few error bands. So what do we mean by error bands, right? So error band basically means the difference between the steady state value and its desired steady state value, right? Desired value that I want to reach. Okay, basically this is the steady state value, but obviously to reach this one I need infinite time. So obviously I won't wait for that. I want some closer value to this one, so that that is enough, that will be good enough for my system to work. Okay, so that value will be good enough. So here like css is known as the steady state output. Okay, and this is equals to c infinity, basically final value. So the 1% error band, what does it mean? 1% error band means I am within 99% of the c steady state, right? So if at whichever time I reach 99% of my steady state value, that time will be known as the settling time for 1% error band. Okay, now for 2% error band, 98% of the c steady state, that is I have 2% error from the steady state value, right? 2% error from the steady state value. Now what is the 4% error band? 4% error band means I am within 96% of my steady state error value, and 5% means I am within the 95% of the steady state value, right? So yeah, all these are this. Okay, so like I will derive for one, another one you derive, right? Because deriving for everything is just a waste of time. You can derive, right? So like what are the like standard? What is the standard? Standard is this 2-1, right? Okay, let me. Standard is this 2-1, right? 2% error band is standard. If nothing is set, we will find the 2% error band settling time. So let me write settling time. Okay, so this is the main thing basically. So yeah, now let's calculate the settling time basically. So I'm calculating for 2% error band. So for 2% error band, I have my C of t equals to, again the same thing, ak into 1 minus e raised to minus t upon tau. I hope you're understanding why am I writing ak, because I want to prove it for generalized case, any magnitude of unit step and any tc gain of the system. So this will be basically 0.98 times ak, that is a steady state value, which is equals to ak into 1 minus e raised to minus t settling. So this is for the 2% error band, right? Okay, 2% error band. So already Himanshu has taught you, like he has taught you there that the t settling is 4 tau, right? 4 tau. So this will be 1 minus t settling by tau equals to 0.98. So e raised to power minus t settling by tau equals to 0.028. So basically, right, what I can see is t settling equals to tau ln 50. Okay, so this is my t settling. So this will be approximately equal to 4 tau. Okay, so that's why we study in transient, right? But that my output reaches 98% of its steady state value at 4 tau time. So that's why I tell all this, right? So yeah, so this one you have to remember that, like we anyways remember this, right? This is the basic one. So okay, where am I? Sometimes this, like this tab just close up. T settling equals to, this is 2% error band equals to 4 tau. Okay, now if you do the same for the 5% error band, what do you get? What you will get? This is by default, this is default parameter. Okay, by default we'll choose this one. Okay, so for 5% error band, what happens? For 5% error band, right, my settling time changes to basically 3 tau. Obviously time will get reduced, right? As the error band is more, I will reach my desired output lesser time. It will take less time, right? As I want less output to be reached. Okay, response amplitude will be less. So this is 3 tau and this is for 5% error band. So if nothing is specified, okay, we'll choose the 3% one, 2% one. Now if it is specified, obviously you can calculate, or you don't have to remember. I will recommend not to remember, just remember these two. Okay, or if you don't even want to remember these two, just remember this one is the most important one. Another one you just derive. You see like how much time it took me to derive, just seconds, right? I'm writing all this, that's why you don't even need to write all this. You can directly go here, right, or here. Okay, and then you put it in the calculator and you will find your value. So yeah, that's what we did. Okay, so basically, right, we studied what we studied in this lecture. We studied basically the effect of zeros. Okay, what does the effect of zeros do? It characterizes the dynamic behavior of the system. It changes the dynamic behavior, right? So if I add a zero, it tries to nullify the effect of a pole, right? So as this zero is getting closer to this pole, this is trying to cancel out this pole, right? As I reach at this pole itself, then the pole zero cancellation will occur. But if I reach closer to this pole, what this zero is very evil, right? It will try to make this pole disappear. Okay, so evil zero. So that is what this is doing, basically reducing the dominance of the pole, right? Okay, so let me write the dominance in a better manner. This is dominance of pole has reduced. Okay, so yeah, this was basically this. And if I have right hand side zeros, what will happen? It will cause my response to change its sign. Okay, suddenly. So yeah, my response will change its sign. So that is also bad, right? I don't want my response to changing sign if like it's like in a motor or something. Okay, so then we studied the parameters of first order system, which are very simple: delay time, rise time, and settling time, right? So rise time was basically for this definition of first order system for a unit step input. The definition is it reaches from 10% to 90%. That is known as the time taken to reach from 10% to 90%. That is known as the rise time. The time taken to reach from to reach from 0 to 50% is known as the delay time. Okay, and the time taken to reach from 0% to whatever error band I want is known as the settling time. But by default I will choose the 2% error band if nothing is specified, but if something is specified, obviously I will calculate. Okay, I will calculate. So these things you don't have to remember, these things you can derive in seconds, but the second order case you have to remember a few things. Okay, so you can keep your storage memory free for those ones. You don't have to remember this, you can derive this. Okay, yeah, thank you for watching.